So if we think about vectors and kind of how we've worked with them, we've always dealt with vectors that go in one direction. Like we're looking in the x direction or the y direction. And when you deal with vectors that way, you really just have to pay attention to the direction of the vector. We've got a positive direction and a negative direction. And you're just adding up the values of the vectors directly, like you would ordinarily adding up numbers. So we're going to start by looking at displacement vectors, because displacement vectors are really easy to visualize. But the skills and the concept behind displacement vectors works for any kind of vector. So velocity vectors, acceleration vectors, force vectors, and so on. So if you considered someone walking around a room, a person walks 8 meters to the east and stops, and then they walk 4.5 meters again to the east, it's pretty easy to realize that their total displacement, their net displacement, is 12.5 meters to the east. You just add up the numbers, right? 8 plus 4.5 is 12.5. So that's easy. So one way you could represent that is graphically, using arrows to represent each individual vector. Okay, so the two vectors representing a person's displacement could be drawn like this. And I've set up this handout so that it's drawn to scale. So if you're looking at the handout, 1 centimeter should actually equal 1 meter. And I forgot to give you rulers, but I'll get you those in just a second. So the two displacements, the two separate displacements, could be represented like that. 8 meters to the east and 4.5 meters to the east. So the method to adding these two vectors graphically is something that I call putting the vector's tail to tip. Okay, so we had our 8 meters. If you take the second vector and kind of slide it over tail to tip of the first vector, what you would have is something like this. Okay, basically you've put the two vectors together. So you've got 8 meters and 4.5 meters of displacement, and the net displacement, and this always works whether or not the vectors are in the same direction, different directions, crazy directions. The vector representing the net displacement can be found by drawing a new vector from the tail of the first vector to the tip of the second vector. So that would look like this. Okay. So you know it, you don't need to measure it. If you measure that, it's going to be 12.5 centimeters long, meaning that the net displacement, the overall displacement, is 12.5 meters to the east. Okay. So we're setting this up with a really simple case, and then we're going to see if this works, and we'll see that it does work for more complicated cases also. So again, that new vector, that long vector, is the net displacement, 12.5 meters east. Okay, so just showing that it does work if two vectors are in opposition or in opposite directions. Let's think about a new situation. Person walks 14 meters to the west, then turns around and walks 11 meters to the east. Again, you wouldn't need to draw a picture of this. You can probably figure it out in your head what the net displacement is, but just to kind of prove to you that this still works. 14 meters to the west could look like this as a vector. 11 meters to the east could look like this. And again, using this tail to tip method, we're going to slide the second vector tail to tip to the first vector. So here's our first vector, and then if we slid this 11 meter east vector to its tip, it would look like that. In the overall displacement, again, you start from the tail of the first vector and you draw a new vector to the tip of the second. So the net displacement, as you probably already knew, was 3 meters to the west, because you walked off 14 meters to the west and you only came back 11 meters. So the net, or kind of the sum of the displacements, is 3 meters to the west. Okay, so those two simple cases are just to set up the idea behind this tail to tip addition of vectors. So it gets more useful when you look at vectors that are not in the same direction. Okay. The next simplest case we could look at would be when two vectors are perpendicular. Okay. So now a person walks due north 5 meters. That's this vector. And then turns left and walks due west 3 meters. Okay. If we want the net displacement, displacement is change in position, so it's not distance covered, right? The distance they covered is 8 meters if I just add up 5 and 3. I want to know what's the actual change in position, like on a grid. If I want to know how far did he move from here to here, we've got to do some geometry to figure that out. We can use the same technique, though. The net displacement would be found by drawing a new vector from the tail of the first to the tip of the second. So that would look like that. Okay. Now, if you're drawing this to scale on a sheet, you could just go ahead and measure that, right? Measure it in centimeters. And because everything is drawn to scale, you should get a pretty good idea of what the displacement is. Okay. We'll also check it mathematically to kind of verify what we expect. Okay. So looking at what we've created here, we've got a right triangle, right? So we can use Pythagorean Theorem to work with these three vectors. This is a right angle in here. Okay. So thinking about it, Pythagorean Theorem tells us that a squared plus b squared equals c squared, where c is your hypotenuse. In this picture, this is your hypotenuse, right? Because this is a right angle. So I'm going to walk through this in a bunch of more steps than you would probably show, but just to walk through to completion. A and B would be my sides of the triangle. Should equal c squared. We've measured it so we could approximate it, but we want to know exactly what is c. So it's kind of like our unknown. And then we just need to go through and work out the algebra to solve for c. Now what I've done here in this next step is square the number, but also square the unit. Okay, so 9 meters squared plus 25 meters squared should equal c squared. Or 34 meters squared equals c squared. And then solving for c, I need to take the square root, right? And my answer comes out to be about 5.8 meters equals c. When I take the square root of 34 and the square root of the unit, things work out as expected. I end up with meters as my unit. So that represents this length. Okay. So the overall displacement was not 8 meters, not just the regular sum of these. It's the vector sum, meaning the sum paying respect to direction. Okay. I could even go back at this point and figure out, say, like what this angle was here if I wanted to. So again, you kind of work with your geometry skills to figure out exactly what's going on. Okay, so maybe you have vectors, though, that are neither parallel nor perpendicular. This would be kind of like your most complicated case. What we tend to do here is actually break a single vector into an equivalent pair of what we will call component vectors. Okay, so maybe you have a vector at an angle. You want to know how much of that angle is on the x-axis and how much is in the y-axis, or how much is in the x direction and how much is in the y direction. That process of finding the components is called resolution of vectors or decomposition of vectors. You'll see both in various textbooks. It's kind of like breaking the vector apart into its pieces. Okay, so let's think about how this might work for a force vector. So think of a person pulling on a string that's connected to a box. The box has a mass of 5 kilograms. The string is pulled 25 degrees above the horizontal with a force of 55 newtons. The box does not move. So we know that there must be some static friction involved here, or the box would accelerate if you applied a force to it. So let's start with this tension force, because it's kind of like the most complicated force in this example, because it's at an angle. It's 25 degrees above the horizontal. So you could represent that. First, represent the object as a dot at the middle of our force diagram. And then the force vector is 25 degrees, so not quite 45 degrees, but 25 degrees above the horizontal, and it has a magnitude of 55 newtons. Now we could try to draw this to scale, and technically you could. Like assign a number of newtons per centimeter or something on your sheet. You don't necessarily need to go that far in most of the examples that you do, but if you try to kind of pay respect to how big the forces are, that's a useful thing to do. So let's think about how we would deal with this vector if we want to break it into two components. First, we know the angle's 25 degrees. And what I really want to know is how much of this 55 newtons is to the right and how much of the 55 newtons is upward. So the way I recommend doing this is to start by lightly sketching a rectangle around the diagonal vector. Okay, so that's going to look something like this. And again, this is where a ruler can come in handy, because you're trying to sketch that out so that it's parallel to your x-axis. This one should be perpendicular to the x-axis. And if you get sloppy with that, sometimes that can lead to trouble. So this is kind of just a way to accurately draw this. So we've got two components to the tension force, one upward, one to the right. The y component, which we could symbolize as F subscript Ty, meaning a tension force in the y direction, would be equal in length to the vertical side of this rectangle we sketched out, right? So it's just as tall as this vector is to the off at its angle. And so I've tried to make the tip of that component exactly as tall as this rectangle. Again, the rectangle lines are just kind of a guide. So the x component of the tension force, or Ftx, would be just as wide as this vector is. So it would look like this. The tip of that vector goes right to the edge of that rectangle that we've drawn. So you want to be careful drawing these, because what I'll see a lot is students will get kind of sloppy and they'll make this vector too long and this vector too long. The reason why we want to draw it precisely like this is if you think about this tail to tip method, if I put those two vectors tail to tip, they should end up exactly where the original vector ended, okay? Because really what we want is two vectors that add up in a vector sense to equal our angled vector. Okay, so I'll show you that again. If you've drawn this properly, if you put the two vectors tail to tip, it ends up like this. Okay? All right, so moving on. If we want to find the magnitude of the y component, so the length of this vector, what I would suggest using is sine function. Okay? So remembering back to your geometry, sine, cosine, tangent, they're really useful in these types of cases, right? Sine is always a ratio of opposite side to hypotenuse, right? Cosine is always a ratio of the adjacent side to a hypotenuse. And tangent, if you need it, is opposite over adjacent. Okay? So we're going to work with this 25-degree angle. We've got a right triangle because we know that this is a right angle. So essentially we've got a hypotenuse, we've got an adjacent side, and we've got an opposite side. Okay? So I'm suggesting we use sine to find the y component, that would be the length of this, because the opposite side of that 25-degree angle is going to be congruent to the length of that vector. Okay, so kind of setting this up, probably with more steps than you need. Sine of 25, because it's opposite over hypotenuse. The opposite side is congruent to FTY, so I've plugged that in. The hypotenuse, again, the hypotenuse is the full 55 newtons of force. So we've got this set up. And then we just work through the algebra to find what the value of FTY is. So rearranging it first, and again, you probably wouldn't show all these steps necessarily when you do it on your own. We want to multiply both sides by 55 newtons. So what we're really saying is FTY equals 55 newtons times the sine of 25. Okay, we plug that into our calculator, and rounding to 2 sig figs, we should get 23 newtons if you walk through it. One thing to be careful of when you're solving this sort of problem, in physics, usually you're given your angles in degrees, at least for this type of problem. And in math, you might be using radians for your angles. So just make sure your calculator is set to degrees rather than radians, where your answers might get off. So if you're ever doing some problems and your answers just seem crazy, you're probably in radians on your calculator instead of degrees. Okay, so that 23 newtons would be right there in my diagram. We're going to do something similar with the x component, but we're going to use cosine because we're dealing with the adjacent side to the 25-degree angle. Okay, so the setup, now cosine of 25, which is adjacent over hypotenuse, is ftx, the x component to the tension, over the 55 newtons. Again, multiplied by 55 newtons on both sides. And walking through the steps, we should find that ftx is right around 50 newtons of force. Okay, so in our diagram, that's here. Okay, so it should make sense that the x component to this force is greater than the y component, because it's a 25-degree angle, right? More of the force is to the right than upward. You know, if it were a 45-degree angle, we would expect both components to be the same. If they're greater than 45 degrees, then the y component should be greater than the x. Okay. All right, so moving on, how do we fit this all together with the rest of the problem? That's just one of the forces acting on the box. We might be interested in knowing what is the magnitude of the static friction on the box. What's the magnitude of the normal force on the box? So let's fill in the rest of the force diagram. Keeping in mind that we really are showing just one force here, I like to use dashed lines for components because they're really not separate forces. They're forces that would add up to give you this angled force. Okay? So some other actual forces here would include the force of gravity, or F subscript g, which would be downward, right? So we can draw that starting at the object straight down on the y-axis. And we know that the force of gravity is g times mass, right? That's what we found out in our previous lab. So the original problem said it was a 5-kilogram object, so 5 kilograms times g, or 5 kilograms times 9.8 newtons per kilogram, gives us a gravitational force of 49 newtons. Okay, a couple ways you can think of it. Some people like to just work with magnitude, so they keep all of their forces positive, and they're just thinking about the length of the vector. So you can think of this downward vector as 49 newtons of force downward, or some people prefer to consider that a negative force because it's in the negative y direction. again, I'll leave that up to you as to kind of how you want to handle that. We would expect there to be some static friction also, because it said the box didn't move, okay? So that's the direction of motion would be to the right if it were going to move, because we're pulling it to the right. So the static friction is resisting that to the left. And I would expect in the x direction for forces to be balanced, because there is no acceleration. So that's why, kind of in preliminary sense anyway, I'm trying to draw that vector the same length as the ftx vector. We would also expect there to be some normal force, because even though we're, in a sense, lifting the box when we pull it up at an angle, we would expect that it's still interacting downward with the surface, so the surface is pushing back up. And until we do a little more work, we don't really know how long to draw that vector, but we know that it should be upward, because it's created from the surface pressing up on the object. And so that fills out our force diagram. We've got our angled pull, we've got a normal force upward, we've got static friction resisting to the left, and gravity pulling downward. Okay. So a couple of things we've kind of already talked about. We know the box is not accelerating. So we know that the net force acting on the box is 0. In other words, all of these forces must actually be balanced, right? There must be, what we should see is the sum of all the forces in the x and y direction should be 0. Okay, that's one way to think about it. So in the x direction, one way to represent this would be to say the x component of the tension, this rightward force, plus static friction must add up to 0. That's one way to say that these forces are balanced. When you take this approach, you would want to realize that ftx is positive, the static friction force is negative. Okay, so looking at what we know, we already calculated that ftx was 50 newtons to the right, so it's a positive 50 newtons. Static friction is kind of like our unknown, although it's pretty simple to figure out what it is. So proving this algebraically, I guess if you solve for FSF, the static friction, it must equal negative 50 newtons. The negative here just means it's to the left. Okay, so we could add that to our diagram. Some people prefer to look at this kind of in a magnitude sense. So maybe you're not going to worry so much about this being negative. If you're setting it up that way, you would probably just say the magnitude of ftx equals the magnitude of the static friction force. Okay? And because we know that ftx has a magnitude of 50 newtons, that must also equal the magnitude of FSF. Okay? And it's just kind of your preference. Some people like to work with the negative sign, some don't. It's up to you to decide how you want to handle that. Okay? The y direction is a little bit trickier because we actually have 3 vectors to pay attention to. We've got the 23 newtons of upward tension force. We've got the 49 newtons of downward gravitational pull. And then we're trying to figure out how much normal force must be present. Okay, so let's take the approach where we're kind of assigning positives and negatives first. We could say that Fty plus the normal force plus the force of gravity equals 0. Okay, so some of these are positive, some of them are negative, but when you add them all up, you have 0 net force because the box is not accelerating up or down. So plugging in our knowns, the y component to the tension, so the piece of that tension force that's upward, is 23 newtons, and it is positive. Normal force is our unknown. The force of gravity, we would want to plug it in as negative 49 newtons because it's downward if we're using this approach. And all of that should equal 0. So from here, it's just algebra. We want to solve for normal force. We could add together 23 newtons plus a negative 49 newtons to get negative 26 newtons. That all equals 0. And then solving for normal force, of course. 26 newtons. It would be positive if we follow the algebra through, right? Which makes sense because the normal force is upward. Okay. So that shows, once I know that, I should probably adjust my force diagram because the normal force is actually greater than the y component. So you could kind of fix your diagram if you're trying to make it kind of semi to scale. It should actually be a little bit longer than the other vector. Not a big deal if you didn't do that, but that's something we can consider. Now, if you take a magnitudes approach, the way I would set it up is say that these two forces together must equal the size of the force of gravity. So you could say something like the force of gravity magnitude equals the magnitude of Fty plus the magnitude of the normal force. Okay. So the magnitude of the force of gravity is 49 newtons. The magnitude of Fty I figured out using my geometry, 23 newtons, plus the magnitude of the normal force, which is like our unknown. Okay, so solving it that way, now I'm going to subtract 23 newtons from both sides of the equation, and I'm going to get the same answer, that the magnitude of the normal force is 26 newtons. Okay, so again, you might play around with it, decide which one you like the best. Either approach does work.